Last time, we proved something strange and beautiful. That king minus man plus woman lands right next to queen. Meaning, it turns out, is geometry. Every word is just a vector, a point in space. And we left you with a question. If those vectors could somehow read a whole sentence and let the words talk to each other, a machine could actually understand it. So here is a sentence. The animal didn't cross the street because it was too tired. Quick, what does it refer to? The animal or the street? You knew instantly. The animal, obviously, because streets don't get tired. But freeze on that little word, it. On its own, the vector for it is identical in every sentence. It carries no idea of what it points to. It is genuinely stuck, flickering between two possibilities, until it does the one thing you just did without thinking. It looks around the sentence and figures out which word it belongs to. That looking around has a name. It is called attention. And here is my promise to you, by the end of this video, you will understand the one formula that runs every large language model on Earth, the actual T in GPT, not as scary symbols, but as something almost obvious. I don't say that lightly. The paper that introduced this formula has been cited over 250,000 times, one of the most cited papers of this century. So, here's how we'll earn it. We're going to walk one single word through the whole machine, watch a grid light up cell by cell, and by the end, you'll also know exactly why your 50-page PDF makes a chatbot crawl. One word, one grid, one formula. Let's begin. First, let's be precise about the goal, because most explanations fumble this. Attention does not summarize the sentence down to one thing. It takes in a row of word vectors, and it outputs the exact same number of vectors. Same shape, in and out, but every vector that comes out has been updated to include context from its neighbors. Think of it as a refinement step. The word it walks in confused, and it walks out knowing it means animal. In, context, out. That is the entire job. Now, how does a word actually pull meaning from another word? Let's bring back the cloud of meaning from last episode. Every token in our sentence is a vector, an arrow pointing somewhere in this space. Watch them light up the animal, street, it, tired. They sit scattered across the galaxy, each one a learned point. Now let's flatten that picture, line the words up left to right as a neat row of vectors, and zoom in on just one of them, our troublemaker, it. Everything that follows happens to this one word first. Once you've seen it happen to one, you've seen the whole sentence. Here is the heart of it, and the part that trips absolutely everyone up. So slow down with me, because once this clicks, the rest is easy. Each word's vector is going to put on 3 different hats, not 3 different words. The same vector multiplied by 3 separate learned matrices, producing 3 new vectors. We call them query, key, and value. 3 hats, 1 head. And the whole trick of attention is that these 3 roles do 3 completely different jobs. Let me give you the cleanest way to think about them. Picture a dating app. Your query is your search, what you're looking for. The word it is a pronoun, so its query basically says, I'm looking for a noun I can attach to. Every other word also carries a key, like a profile headline advertising what it is. Animal's key says, I'm a thing that can be tired. Street's key says, I'm a place. And finally, every word has a value, the real content it hands over once it's chosen. The key is how you get found. The value is what you actually give. Keep that split in your head, advertise, then deliver. Now let me make that rigorous with an analogy from the field's own textbooks, one most explainers skip. Attention is a soft dictionary lookup. A normal dictionary, or a hash map, takes one exact key and returns one exact value. Attention is fuzzy. Your query is compared against every key, and instead of one answer, you get back a blend of all the values, weighted by how well each key matched. Not the answer. A weighted summary of every candidate answer. And that softness, that blending, is exactly what makes it learnable. Hold that thought, it pays off in a second. And here's the part that should give you chills. Nobody programmed those 3 matrices. Nobody wrote a rule saying pronouns should look for nouns. Remember the ball rolling downhill from way back, the predict, blame, nudge loop? Those query, key, and value matrices are learned by that exact same gradient descent. The model is shown mountains of text, it guesses, it's told how wrong it was, and it nudges. Out of that grind, all on its own, it discovers that it should hunt for animal. The grammar emerges. It was never written down. So we have 3 hats. Now let's actually use them. Take the query of it and the key of animal, two vectors. To measure how well they match, we use the dot product. Don't panic, it's simple. You line the two vectors up, multiply them component by component, and add it all up. When two vectors point the same way, the dot product is big. When they're perpendicular, it's near zero. So it is just an alignment meter. Query of it, dotted with key of animal, the needle swings high. They match. Now do the same for the others. Query of it, dotted with key of street, the needle barely moves. Low score. Dot it with cross, with tired, and you collect a whole row of numbers, one relevant score for every word in the sentence. That row is it, asking the whole room, how relevant is each of you to what I'm looking for? High for animal, low for the rest. One word, one row of scores. Simple. But watch what happens when we do this for every word at once. This is the moment everything snaps together, so watch closely. That row of scores we just built for it? Slide it into the top row of an empty grid. Now do the exact same thing for every other word's query, and let each result drop into its own row. The grid fills in, cell by cell, row by row. And what you've just built, from one row you watched get made by hand, is the famous attention matrix. Every cell asks one thing: how much should this row's word pay attention to this column's word? In math, this whole grid is Q times K transpose. Q, K transpose, the hero of the entire story, and you just arrived at yourself. And right here, staring at this grid, is the most expensive fact in artificial intelligence. Every word compares itself to every other word. So if your sentence has n words, this grid has n times n cells. Double the length, and you quadruple the grid. For a prompt of 128,000 tokens, this single grid holds over 16 billion cells. That is why you can't just paste your whole book into a chatbot. That is why long prompts cost more and answer slower. We'll come back to this wall. For now, just remember, every glowing cell costs something. Quick stability fix, and I'll keep it short because it's a footnote, not the plot. As vectors get longer, their dot products get bigger, just from having more numbers to add up, not because the words matched any better. Dot 2 short vectors, and you might get 8. Dot 2 longer ones, and you get 20, for no real reason. If we feed those bloated numbers into the next step, training stalls. So we divide every score by the square root of the vector's length, 64 in the original model. The numbers calm down, learning stays alive. Watch the grid cool to a tamer range and move on. Now the magic step, and this is where attention becomes a real decision. Our scores are still just raw numbers. We want percentages, a clean answer to where should it spend its attention. For that, we meet a function called Softmax. It's brand new to us here, and we'll lean on it again later when the model finally picks its words. Picture a classroom. It asks a question, and every word raises a hand at a height equal to its score. Softmax looks at all the hands and turns them into shares of the floor, percentages that all add up to exactly 100%. Bigger score, bigger slice. That clean split is what turns a pile of raw scores into an actual decision. And here is the detail that almost every explainer gets wrong on screen, so let's get it right. Softmax happens per row, not across the whole grid. Watch only the it row. Its cells recolor and rescale until that single row sums to exactly 1. The animal cell lands around 80%. The street cell, a tiny 5. Crumbs everywhere else? The word it now spends 80% of its attention on animal. Then every other row independently does the same, each word distributing its own 100%. The formula assembling above the grid now reads softmax of QK transpose over the square root of the length. Match, then normalize. We have the percentages. Time for the payoff. It rebuilds itself. Take those weights, 80% on animal, 5 on street, and the rest, and use them to mix the value vectors, the actual content each word hands over. 80% of animal's value, a sliver of streets, a dusting of the others, all summed into one brand new vector. Because animal dominates the blend, the new vector for it now points mostly toward animal's meaning. It has literally absorbed what animal is. And the complete formula is now fully earned, every symbol explained, attention equals softmax of QK transpose over root length times V. Match, normalize, blend. Let's go back to the galaxy of meaning and watch this land. There floats the old vector for it, sitting in some neutral, confused spot. Now we apply the blend. and the point drifts, gliding across the space, pulled toward the region where animal lives until it parks right beside it. That movement is the whole episode in one shot. The word it walked in not knowing what it meant, and it just walked out meaning, roughly, the animal. Not because anyone told it to, because it looked around, scored its neighbors, and rebuilt itself from the one that mattered. That is understanding, made of arithmetic. Now zoom back out, because here's why this design conquered AI. We just walked through it for one word, one row. But that single matrix equation does it for every word at the same time, in one parallel shot. The whole sentence updates itself in a single sweep. Contrast that with the old way, the models before this, which read strictly left to right, one word at a time, and forgot the start of a long sentence by the time they reached the end. Attention lets every word see every other word at once. That is why transformers trained so fast on graphics chips, and why everything before them was swept away. One GPT-specific twist, because we're building a GPT and a GPT writes text. When it's generating, a word is predicting what comes next, so it must not be allowed to peek at the future. The future hasn't been written yet. We enforce that right on the grid. Before Softmax, we take the upper triangle, every cell where a word looks ahead, and shove it to -infinity, so Softmax crushes those weights to 0. Watch the top right half of the grid go dark in a clean diagonal staircase. Now every word can only look backward, at itself and what came before. That single dark triangle is the difference between a model that reads and a model that writes. Now let's come back to that wall I promised, the n times n grid, because it shapes the entire industry. Doubling your context window quadruples the compute and the memory. That square is the real reason context windows were stuck small for years, and why long context is a feature worth billions. An entire branch of research exists for the sole purpose of dodging this one matrix: flash attention, sparse attention, sliding windows, state space models. Thousands of researchers paid to avoid building the full grid. The thing you now understand in your bones is the exact bottleneck they're all fighting. Let's lock it in, because you just learned the engine of modern AI. Remember that confused little word from the start? It, flickering between the animal and the street? Here's exactly what saved it. 1. Every word puts on 3 hats: a query for what it wants, a key for what it advertises, a value for what it gives. Match. Each query dots against every key to score relevance, filling that grid, QK transpose. 3. Normalize. Softmax turns each row into percentages that sum to 1. 4. Blend. Each word rebuilds itself as a weighted mix of values, heavy on what it matched. Match, normalize, blend. That is the whole T in GPT, the formula behind every model you've ever used, and it is exactly what let it find the animal. But I've been hiding something, and it's the perfect cliffhanger. The head we just built learned one relationship: pronoun finds its noun, it points to animal. Yet it also relates to tired, the reason it didn't cross. A single head can't track both at once. So real models run a second head in parallel that locks it to tired, and a third, and a fourth. GPT-3 runs over 9,000 of these little looking around operations at the same time, each in its own subspace, each catching a different kind of relationship. Watch a second grid slide in, then a stack of them fade back into the distance. And that's the beautiful problem we end on. One head sees one kind of relationship. Real models run dozens, all at once. And then they have to glue those dozens back together into a single answer, and stack the whole apparatus dozens of layers deep, one on top of the next. We've built one perfect brick. Next time, we turn that brick into a machine that actually generates text, the transformer block, attention, and a small network, fused, normalized, and stacked into a tower with a glowing highway running up its spine. You've understood how words talk. Next, we make them speak.